Hello. In this video, we're going to look at how we can use vectors to represent lines in 2 dimensions and more importantly in 3 dimensions, because we already have a lot of ways to represent lines in 2 dimensions. But let's start in the Cartesian plane, so 2 dimensions. We can define a line by using a slope, which corresponds to a direction, and a point, which corresponds to a position. Vectors can give us the same information. We can have a position vector that tells us where we're starting or a point on the line. And the slope can also correspond to a direction vector. So lines can have vector equations in addition to their Cartesian equations. So for 2 dimensions, we're very familiar with Cartesian equations. And we're going to look at the relationship between the Cartesian equations and vector equations. And then this will allow us to extend into 3 dimensions and figure out what a Cartesian equation would look like in 3 dimensions. So starting with a vector parametric equation. So essentially what I have here is I'm saying v is representing the position vector of any point on the line. So this will be essentially the coordinates of a point on the line. So position vectors of points on the line. A is going to represent a position vector of a known point on the line. Now here's where this is different from Cartesian. Well, I mean, it's not, because we could have infinitely many starting out for position vectors of points that we know are on the line. So we can have infinitely many parametric equations. Any point on the line will do for A. So this is some point on the line. So some position vector on the line. T is a scalar, and that is our parameter. That's the thing that changes. It's kind of the x value of this equation. So for various values of t, often we use t because we're talking time, because vectors can often be representing a displacement in time. So we'll have a line that maybe is for values of t that are greater than or equal to 0, where our starting point is the position at time 0. And then this equation for various values of t, whether that's seconds or hours or whatever, will give us the position at that time. But it doesn't have to be for time. And then d would be the direction vector, essentially the slope. It tells us the direction that the line is going. So in 2 dimensions, it works exactly the same as in 3 dimensions. So we're going to just jump into a 3-dimensional example. I have a 3D point and a 2D point, and I know that I have a line that connects them. Now, I don't know which of these is the starting point. Either one could be, neither one could be. It doesn't really matter because, like I said, t doesn't necessarily have to be time that starts at 0. It's just some parameter. But I do need a direction vector. So direction vector is going to be either of the two directions from A to B or from B to A. So I can say this is the vector AB, in which case it's 0 minus 1, 2 minus -5, -7 minus 3. Because when I'm going from A to B, I have to figure B is my finishing point. So the displacement that I had from A to B is the component of B minus the component of A. It could just as easily, so I won't continue to do this, but D could be the direction BA, which is going to be exactly the same thing except the opposite. So instead of going 0 minus -1, I go 1 minus 0, -5 minus 2, and 3 minus -7. So the direction vector is essentially just the opposite of the other direction vector. So the parameters would be different to give the same points, but it will still define all the same points on the line. And then for the actual line, I can use either A or B's position vector to be my A in this equation. So for example, V is, the position vector of A is 1, -5, 3. Again, I could just as easily be using 0, 2, -7, does not matter, plus some parameter times either one of these two direction vectors. Does not matter which one. This is a parametric equation of that line, but there are multiple options for this. Now to find that Cartesian equivalent, I'm going to essentially use the parameters of each component. So I say, well, okay, assuming that V is some x, y, z, because V is a position vector of every point on that line, and every point on that line has coordinates in the form x, y, z. So that means that x would have to be 1 minus t, because it's 1 plus -1 times t. Y would have to be equal to -5 plus 7t, and z would have to be equal to 3 minus 10t. So each coordinate has to come from combining the corresponding coordinates from that parametric equation. But all of these t values have to be the same. So if I rearrange each of these equations to isolate t, so t equals 1 minus x, t equals y plus 5 over 7, or t has to equal, I'm going to call it 3 minus z over 10. It could be z minus 3 over negative 10, doesn't really matter. Each of these statements has to be equal to t. So the equation of this line, the Cartesian equation of this line in 3 dimensions, is a multi-stage equation. It has 3 parts. 1 minus x equals y plus 5 over 7 equals 3 minus z over 10. So the equation of a line in 3 dimensions needs these 3 parts. It's actually kind of 3 separate equations. One that relates x with y, one that relates y with z, and one that relates x with z. Now, in 3 dimensions, we have multiple options for intersections of lines. So in 2 dimensions, you have 2 options. Either the lines intersect, well, I guess we have 3 options. Either the lines intersect exactly once, or they are the same line, coincident lines, or they never intersect, in which case they're parallel. We do sort of have those same options in 3 dimensions. The lines could actually be the same line. They might be coincident. They might meet exactly once, or they might never meet. But if they don't meet, it doesn't necessarily mean they are parallel. Parallel means they have to have parallel direction vectors. But in 3 dimensions, it's entirely possible for like a line to be going like this, and then another line to kind of pass by underneath it in a different direction. These lines are called skew. So lines can still be parallel and never meet in 3 dimensions, but just because they don't meet doesn't necessarily mean they're parallel. So we're going to look at 2 lines here. We have a plane flying such that its position at t seconds is given by this first equation, and a second plane's position given by the second equation. And I want to know if the plane's trajectories cross. Now there's actually kind of 2 possible questions I could ask here. One would be, do the planes crash? That would mean they have to arrive at the same point at the same time, and that's a slightly more complicated question. Do their trajectories cross just means, do they ever go through the same point, even if it's not at the same time? So I cannot assume that the time coordinate is the same for each of these planes. So what I'm going to do is I'm going to rewrite this second one using a different parameter. So u equals negative 12, 4, negative 2, plus s, 5, negative 2, 5. Because I don't necessarily know that they're at the same time that they would meet. Now, if I was asking, do they crash? Then yes, it would be, do they reach that same point at the same time? But I don't know that here. So I have to sort of think, is there a point where they meet? And let's call that point M. I'm going to call that position vector of that point M, X, Y, Z. So what I want to know is there some value X, Y, Z such that that point lies on V and lies on U. So from the first equation, I get that X would have to equal 5 minus 6t. But from the second equation, from u, I get that x would have to equal negative 12 plus 5s. For the second coordinate, the y value, y would have to equal 2 plus t, but y would also have to equal 4 minus 2s. And for the third coordinate, I get that z equals 7 plus 4t, but z also has to equal negative 2 plus 5s. So now I have 6 equations with 5 variables. I'm going to deal with each one sort of individually. I'm going to first leave z off. I'm going to use z as my check because these first 4 equations with 4 variables are completely solvable as is. So I can write 2 equations with just t and s. So that's 5 minus 6t equals negative 12 plus 5s because, of course, x equals x. So that means that 17 equals 5s plus 6t. And in the second one, 2 plus t equals 4 minus 2s, which means that, let's go 2s plus t equals 2. So solving this system, I'm just going to solve it using a matrix. So I'm using a matrix that is 2 by 3, in which I have 5, 6, and 17 for the first row, and 2, 1, and 2 for the second row. And then, of course, using the reduced row echelon. Your calculator may have a slightly different way for solving this, or you can just do it algebraically if you like. But if I solve this now, I get that, let's see, t equals -5/7 and s equals 24/7. So right off the bat, I can tell that this isn't at the same time. So if their trajectories do cross, it's not at the same time. So these planes definitely don't crash. But now to check if this actually works, I go into the next section here for the z's, and I determine, do these calculate the same value of z? Because in order for these to meet, that's what would have to happen. So 7 plus 4 times -5/7 gives me 29/7. So z equals 29/7. And in the second one, -2 plus 5 times 24/7 gives me 106/7. So they do not meet. Those trajectories never cross. Now, does that mean they're parallel? Well, no, because if I look at their direction vectors, the direction vectors are -614 and 5, -25. Neither one of these they're not scalar multiples of each other. So these are not parallel direction vectors. So these trajectories are skew trajectories, and those planes never meet.